Hey, I'm Liam, and this is my DIY variable power supply. To start off, I'll give a quick demonstration of two very simple circuits. So to start that, I'm just going to go ahead and turn it on. And just to note, the display on this power supply is broken, so we're going to see the voltage reading over here. And you can see that as I turn on the supply, the voltage reading jumped up from around 20 millivolts of just leftover charging the capacitor up to 3 volts, and this LED turned on, as well as this indicator light on the power supply. So now we can go ahead and demonstrate that it's working by turning this potentiometer that controls the voltage output. So as I'll turn it this way, you can see just both in the brightness of the LED and in the reading on the DMM that the voltage is increasing. And I can turn it back down and it will go down. So I don't want to blow the LED, but the max output voltage of this is around 12 volts because there's a 12 volt transformer in the power supply itself. So this is my next demonstration circuit, and I'm just going to show that as I turn this potentiometer, the voltage reading on the DMM stays roughly the same. I'll get back to why this is significant in a little bit. Next, I'd like to show you a little bit of what's going on inside the power supply. So to do that, I've unplugged it, and I'm going to take off its hood. So right now it's not screwed on, just for ease of access. And inside is all the circuitry. And it's a bit of a mess, but I can guarantee you that the original power supply wasn't looking great inside either. So right here, you can see the transformer that powers it. It's a 120 volt to 12 volt transformer, which means that it's meant to take in 120 volts and step it down to 12 volts. Then we have the actual circuit board, which you can see here. And this circuit board is actually the brains of the whole power supply. This circuit board is a custom buck converter design that I've made. So with that, let's talk about how you can go about making your own variable power supply. The first step of a power supply is you need some way to take the 120 volts AC out of the wall and turn it into some usable voltage. This is generally going to be a lower voltage DC signal. How I do this in my build is I run the 120 volts mains power through the transformer that I mentioned earlier. Then, the 12 volts AC output of this goes through a full bridge rectifier. The result is a stable 12 volts DC signal. Let's go into how this works a little bit. Transformers are versatile devices that have multiple windings around a common core. The primary winding is the winding that's normally connected to AC mains. The electric field of the variable voltage in this winding induces a magnetic field into the core material, which in most cases is made out of a material with a high relative permeability, normally iron or steel. This then creates a magnetic field in the core, and the magnetic field in the core induces an electric field in the secondary winding, which is normally the output winding, where in this case, we get 12 volts AC. We need a core material with a high relative permeability because this means that we'll get the most possible magnetic flux density in the core, meaning that the efficiency of the transformer will be the greatest possible. In general, there is a direct relationship between the turns in a winding and the voltage across the winding. For example, if the primary has twice the number of turns as the secondary will have half as much voltage induced in it as is across the primary. In this case, since we have 120 volts to 12 volts, the secondary will have 1/10 the number of turns as the primary winding. Now next, a full bridge rectifier is an arrangement of diodes that takes the absolute value, you could call it, of an AC waveform. It then turns this into a DC waveform where components such as capacitors can smooth this into a stable DC output voltage. With that, it's time to discuss how we turn this into a variable output for our power supply. To do this in my case, I use a circuit called a buck converter. Buck converters are essentially smooth PWM circuits. On screen now, you can see a buck converter in both its on and off state for the switch. When the switch is closed, the voltage presented to the positive output terminal of the buck converter is the same as the source voltage of the driving circuit. In this phase, the inductor and capacitor also store energy in their magnetic and electric fields respectively. When the switch is then opened, the inductor and capacitor both try to keep the voltage and current regulated across the circuit, meaning that the current and voltage conditions across the load decrease slowly. Now, when the switch is closed again, the inductor and capacitor will still resist changes of voltage and current, which will slow down the voltage gain across the load. So, the inductor and capacitor essentially act as smoothing devices that smooths out a PWM with varying duty cycle. This means that the output of the buck converter is essentially the duty cycle times the source voltage. So, for example, with a 50% duty cycle and 12 volts in, the output of the buck converter will be 6 volts. However, in real life, we obviously can't just have switches that is controlling the buck converter. We're going to use MOSFETs. This introduces the difficulty of MOSFET driving, because with the high side topology like I've been showing, you need an P-channel MOSFET, which is difficult to drive and requires complex circuitry. However, we can use a low side buck converter topology with P-channel MOSFETs. This is advantageous because it's not difficult to drive the MOSFET. There are some drawbacks, but we'll get to that later. The final step of this variable power supply is to implement feedback, because as I showed earlier, when we turn the potentiometer and change the current draw or the resistance of the load, we don't want the voltage presented on the output of the power supply to change. Therefore, we need to implement feedback that detects if the voltage is changing across the output and stabilizes it. To do this, we need a reference voltage that we can compare to the output voltage of the buck converter. However, the one drawback of a low side buck converter is that you don't change the positive terminal of the output, you change the ground terminal of the output. This is because the positive terminal is always connected through the inductor to the source voltage, but the ground terminal is only allowed to flow to ground when the MOSFET is closed. In my circuit, I use a component called the TL431 to act as a stable reference voltage. The reference voltage of the TL431 is controlled by a potentiometer that I showed you earlier. The reference voltage goes into a non-inverting input of an op-amp, and the inverting input of the op-amp is connected to the ground terminal of the output of the buck converter. We then know that if the output of this comparison is high, the voltage across the buck converter is too great and we must decrease the duty cycle of the PWM. And conversely, if the output is low, the voltage is too little and we must increase the duty cycle of the PWM. The PWM is controlled by an AT-Tiny 85. Normally, AT-Tiny 85s are only capable of a PWM signal up to 500 Hz, but this is not fast enough for a buck converter. By going into the TCCR register for timer 0, which is the timer that I used for this project, I controlled the timer and set it to a frequency of 60 kHz instead of the normal 500 Hz by setting the prescaler value to 1. This means that the frequency of the PWM is the same as the frequency of timer 0 and is not divided like it normally is. The AT-Tiny reads the output of the op-amp's comparison and depending on that value either increases or decreases the duty cycle, keeping the voltage stable across the output of the power supply. And that's it. Thank you for watching.